Hi everybody. This is the answer key audio lecture for the practice exam for chapters 4 and 5. So I just wanted to take the time to walk through how I got the different answers for each question, just to help reinforce the concepts and to help make sure that everybody understands. So first question, when a coin is tossed 3 times, what is the sample space with respect to which side it lands on? So we know for coins that there is a 50-50 chance of getting heads or tails. So our sample space is all the different possible outcomes that can happen as a result of 3 coin flips. So we could have 3 heads in a row, 3 tails in a row. We could have heads, heads, and then tails, or tails, tails, and then heads. We could have tails and then heads, heads, or heads and then tails, tails. We could have heads, tails, heads, or we could have tails, head, tail. And so by working through kind of methodically for either option, you come up with a sample space of 8. And that would be the case for anything that you're doing 3 of. 3 births, 3 coin flips, all of those would lead to 8 outcomes. Okay, so now assuming that heads and tails are equally likely, we're going to find the probability of flipping a coin 3 times and getting heads every time. Well, this is pretty easy since we already have our sample space and we know that this is all the possible outcomes that there are. So we got to look at our sample space and figure out how many times is this criteria met, that you get heads every time. And what we find is that only 1 out of the 8 different possibilities yields getting heads every time. So our probability is 1 out of 8. Oh boy. Hold on 1 minute here. I'm going to move into a different view so it's easier to see. Sorry about that. Let me see if I can expand this a little bit. Okay. Alright, next question. You enter a raffle by purchasing a $5 ticket. Your probability of winning is 1 out of 231 and the payout is 10 to 1. So again, you're going to enter this raffle. You're going to pay $5. Your probability of winning is given to you as 1 out of 231, and our payout tells us that for every $1 we spend, if we win, we're going to win 10. So part A, we need to find the actual odds against you winning. And the way that you would do that, oh no, I just realized I have these backwards. Oh dear. Well, B, what I have here for a solution for B is actually A, and what I have here for A is actually B. So let me walk through it. So first we're going to find the actual odds against you winning the raffle. Well, against you winning is you're going to have your probability of not A, so everything that is not the outcome of A, over all the probability for the outcome of A. So if 1 out of 231 times is our probability of winning, then our probability of losing has to be 230 out of 231 times. So when you do out this math, the 231s in the denominator cancel, and you put a colon between your 2 numerators. So you wind up with an actual odds against you winning the raffle, remember I put this in the wrong place, of 230 to 1. Okay, in contrast with that, if we want to find the actual odds for us winning the raffle, we're going to have the probability of A and divide that by the probability of not A. So it's basically just the inverse of what we did to get our odds against. So we're going to have 1 out of 231 as our probability of A, of winning, and 230 divided by 231 for our probability of not A. So once again, the 231s cancel, and you put a colon between your 2 numerators. So you wind up with 1 to 230 being your odds for you winning, because remember, I have these solutions backwards. Okay, so now that we have that, the question asks us how much net profit would you make if you won the raffle? Well, we're going to win $10 for every $1 we bet. And since we bet $5, we're going to multiply 10 by 5 to get 50. And from that, we're going to subtract our initial bet of $5. So we wind up with a net profit of $45. which would be how much we would actually walk out the door with above and beyond what we came in the door with. Okay, next question. Suppose 100 lie detector tests were administered and the results are given in the table below. 63 positive test results, 37 negative test results, out of a total of 100 test results between the two groups. So this question deals with replacement or without replacement. So it's important that as we look at these different questions that we're noting which one we're dealing with. And so I've chosen to underline them for both of my solutions. So part A says if 2 of the 100 subjects are randomly selected with replacement, we want to find the probability that both test negative. Okay, well, with replacement and without replacement, let's just do a quick review on that. With replacement means that the person gets thrown back into the sample and can be chosen again. So we talked about this, like sometimes if you enter like a raffle, you're eligible for more than one prize. So even if you win a prize on the first round, you're still eligible to be drawn again for another prize later on. So that would be with replacement. Without replacement means that the person does not go back in the pile. And it means that you need to adjust your totals to ensure that you've accounted for the person that you've used. So part A, again, is asking us a with replacement question, meaning that we're going to put the person back into the pile. So we want to find the probability that both people test negative. Well, your first person is going to have a probability of 37 out of 100, because that's how many tested negative out of how many total people we had. So there's person number 1, 37 divided by 100. And we're going to multiply that, because this is the multiplication rule here. We're going to multiply that by 37 divided by 100 for our second person. And the reason why is because with replacement means that we didn't actually use anybody from our negative test results group, because the one person we used here got put back into the pile. And it also means that our total number of people didn't change. So when you do 37 divided by 100 times 37 divided by 100, you get 0.1369, or a 13.69% chance of both people testing negative. Okay, moving on to the second question. Now we're going to have to scroll a little bit here, so I apologize for that in advance, but let's read the question. If 3 of the 100 subjects are randomly selected without replacement, find the probability that the first person tested positive, the second person tested negative, and the third person tested negative. Okay, so here we're dealing without replacement, meaning that we do need to adjust our totals as we utilize people. So the first person, we want to know that they tested positive. So let's go up to our table, and we'll find that 63 out of 100 people tested positive. So that's going to be person number 1. Person number 2, let's go up and look at our negative group. We have 37 people out of 100 that tested negative. But we used one of these 100 people towards person number 1 that came from our positive group. So this number is now not 100, but 99. So for our second person, we have 37 divided by 99. Now for our third person, this person also, we want to know their probability of testing negative. So we've actually already used one person from our negative group, so this is now not 37, but is instead 36. And we've used 2 people toward our total, one from our positive group and one from our negative group. So our total is now not 100, but is 98. So for this person, it's going to be 37 divided by 98. And when you multiply those together, you get a probability of 0.865, or 8.65%, of having your first person test positive and your second and third persons testing negative. Okay. Now we're going to move into our Chapter 5 material. So this is a probability distribution for the number of male children born in 3 births. So we're going to complete this table and find the mean, the variance, and the standard deviation. Okay, so we're given our x's as being 0 boys, 1 boy, 2 boys, or 3 boys. And we're given their relative probabilities. 0 boys would be a 0.125 probability. One boy would be 0.375, two boys would be 0.375, and three boys would be 0.125. Okay, so our first column here tells us that we're going to multiply our x times our probability of x. So I went ahead and did that for each. So 0 times 0.125 is 0. 1 times 3.75 is 3.75. 2 times 0.375 is 0.75. 3 times 0.125 is 0.375. Then I went ahead and added those all together, and I got a total of 1.5. The sum of this column, which is what the symbol tells me, equals 1.5. All right, so now I want to move on to the next column. This column is asking me to take each x, subtract from it the mean that we calculated, and we'll go back and we'll figure out what our mean was momentarily. And then we're going to square that and then multiply it by our probability of x. So this sum that we actually did here, this x times the probability of x, and getting a total of 1.5, is actually how we calculate our mean. So our mean is calculated by the sum of our x times our probability of x, which is exactly what we have here. So I'm just going to add together all four values, the 0, 3.75, 0.75, and 0.375, and from there I get my 1.5. So that's the mean that we're going to use to complete this last column here. So we're going to take our x, which in this case is 0, subtract from that our mean, which is 1.5, square that, and multiply it by our probability of x, which is given to us in this column. And when we go ahead and do that for each of our x's, so you'll see there's one for our 0x, one for our 1, one for our 2, one for our 3. Then we're going to total those values together, and we'll find that it comes to 0.75. Well, that number there, this 0.75, or the sum of our x minus our mean squared times our probability of x, that's actually our equation for our variance. So our 0.75 that we got by adding this column together or doing it this way, you got 0.75, and that's your variance. So to get your standard deviation, it's simply the square root of your variance. So the square root of 0.75 is 0.866. Okay, so that goes through the table and how to complete those problems. There's a second part to this question though. Or actually, no, it's really a separate question. I take that back. So we found for families with 3 children that the mean number of male children is 1.6 and the standard deviation is 0.6. So this is different than the problem above. Be aware of that. They're giving you different values, given values for your mean and your standard deviation. And we need to use those values to find our maximum and minimum usual value for the number of male children in a family with 3 children total. Now, this concept is range rule of thumb, which tells us that we calculate our maximum usual value by doing our mean plus 2 standard deviations, and our minimum usual value by taking our mean and subtracting 2 standard deviations. So here's 1.5, which was our mean, plus 2 times 0.87, which was our standard deviation. So we get a max value of 3.24 male children. And for our minimum value, we have our 1.5, which was our mean, subtracting from that 2 times 0.87, and we get negative 0.24. So this is our maximum value and our minimum value. It's important to note that neither of these values is actually really possible. You can't have more than 3 children in a family with 3 children, and you certainly can't have negative children either, but they actually balance each other out. So anyway, that's how you calculate your max and your min, and again, this concept is called range rule of thumb. Okay, next question. This gets into binomial probability distributions, which is in section 5.3. So when a teenager is randomly selected, there is a 0.92 probability that they have a Facebook account. Suppose we want to find the probability that exactly 4 out of 6 randomly selected teenagers has a Facebook account. First we want to know is, does this procedure result in a binomial? And we want to list out the reasons. Reason number 1 is that it has a fixed number of trials. There's 6 randomly selected teenagers that we're going to poll. 2, the trials have to be independent. Whether one teenager has a Facebook account wouldn't randomly impact whether another teenager would have an account. So we will call the trials independent. Part 3. All outcomes can be classified as success or failure, which is a requirement for a binomial, as we talked about in class. So here, the person's either going to have a Facebook account or they're not. So success would be that they have the account, and failure would be that they don't. And the fourth reason, the probability of success remains the same in all trials. And that probability of success is actually given to us in the problem as 0.92. Okay, so now that we've determined that we do in fact have a binomial, now we're actually going to solve this equation for our binomial. So our binomial equation is the probability of x, and our x in this case is 4, equals n factorial divided by n minus x factorial times x factorial. And then all of that together is then multiplied by your probability of x, or your probability of success rather, raised to the power of x, times the probability of failure raised to the power of n minus x. So first I went through and I defined each of the numbers. So our n is 6, that's the number of teenagers we're going to randomly select. 4 is the number that we're interested in, the probability of exactly 4 teenagers. Our probability of success is given to us in the problem as 0.92, and based on that, doing 1 minus our probability of success, we are able to calculate our probability of failure as 0.08, and we know that that's correct because if we add these two together, they add to 1. So then I just went ahead and plugged everything in. 6 factorial divided by 6 minus 4 factorial, so our n minus our x, times x factorial, 4 factorial. Sorry about that, I made a mistake when I was doing this, so I had to white it out and it doesn't look very clear, so I apologize for that, but that is a 4 factorial, multiplied by our probability of success raised to the power of our x, which is 4, all multiplied by our probability of failure raised to the power of n minus x, which again is 6 minus 4. And when you go ahead and do out all of this math, you wind up with a probability of 0.0749 or 7.49%. Okay. Here is another problem from your binomial probability equations. This gets into calculating your mean and standard deviation based on the special equations that were given to you in the lecture for calculating a mean and standard deviation from a binomial. So your mean is defined as this symbol, which is mu, and it's calculated by taking your n and multiplying it by your p, so the number of trials divided by or multiplied by your probability of success. And your standard deviation is given by this symbol, which is called sigma, and that's equal to the square root of n times p times q. So the number of trials times your probability of success times your probability of failure, all square rooted. So now let's go to the problem and fill in the blanks. So the Eiffel Tower has a 78% recognition rate among adults worldwide. A special focus group consists of 22 randomly selected adults. For such a group, we want to find the mean and the standard deviation. So again, our mean is going to be found by taking our n and multiplying it by our p. So 22 times 0.78 is 17.6, that's our mean. And our standard deviation is the square root of our n times our p times our q. So 22 times 0.78 times 0.22. And that's going to equal 1.943. So there, now we've solved for our mean and our standard deviation for this binomial. Okay, and then we're going to use the values that we calculated above, the mean and the standard deviation, to calculate out our maximum usual value and minimum usual value for those that would recognize the Eiffel Tower. So let's refresh what we did up here. So our mean was 17.16 and our standard deviation was 1.943. So we're going to plug those into our range rule of thumb equations, which gives us our max value of being our mean plus 2 standard deviations, so 17.16 plus 2 times 1.943, and that gives us a maximum usual number of 21.046 people. And a minimum value would be calculated by taking our mean minus 2 standard deviations, so 17.6 minus 2 times 1.943, and that's going to give us a minimum value of 13.114. And that again is range rule of thumb for the Eiffel Tower question. Okay, so that actually completes all of the problems for the practice exam. Certainly, if anyone has questions, reach out to me via email with any questions you may have, and I will be posting the final exam very soon. Thank you all again for such a wonderful semester. I really, really enjoyed having you all as a class, and please do keep in touch. Thanks.